Hi, this is Daryl Lewis-Sandy from Mana. Welcome to the fourth training video in our series about the physical quantity service. The physical quantity service is a GraphQL-based microservice which provides the capability to parse and extract physical quantity mentions from strings, to convert between units of measure, and to perform arithmetic with physical quantities in a way that respects their physical dimensions. This series of videos uses a Workspace Services template, which has all of the exercises for the lessons that we'll be working through. If you've been watching our previous videos and following along, then you have your own copy of this Workspace template and should open it now. If you just joined us, take a moment to clone your own copy of the Physical Quantity Tutorials Workspace. In today's lesson, we'll be creating the parse observed lengths in feet function, which takes an observation which has been encoded in an uninterpreted string value, parses it as if it has dimensions of length, and converts it to units of feet. As with our previous lessons, this knowledge graph comes pre-populated with all the kinds and functions that we're likely to encounter as we're working through this exercise. In addition to creating the parse observed length in feet function, we'll also need to create the constant function foot that returns the string foot. We can see that we're going to be working with the observation kind that we've worked with in our previous exercises, as well as the physical quantity and unit of measure kinds from the Mana physical quantity service. In order to parse the lengths, we can use our parse observed lengths function from lesson 2. The only piece here that's at all new is the convert_to function, which is the unit conversion function from the Mana physical quantity service. In order to understand how we might use this function, let us take a moment to look at the unit conversion features provided by the physical quantity service. The physical quantity service provides 5 functions related to unit of measure conversions. These can be found on the physical quantity service's unit conversions knowledge graph. Let's look at each of them in turn. The first of these functions is the convert_to function, which, given a physical quantity and the surface form of a unit of measure, it will attempt to convert the physical quantity to that unit. If the physical quantity has a dimension that is inconsistent with the unit that you specified, it will return a null value instead. Sometimes we just want to know if a physical quantity can be converted to a unit of measure without actually performing the conversion. For this, we can use the CanBeConverted_to function. Just like the convert_to function, we provide it with an instance of a physical quantity and the surface form of a unit of measure. Instead of receiving a physical quantity back, though, we receive a Boolean, which indicates whether or not the unit of measure and the physical quantity are dimensionally consistent. Since unit conversion is only possible when a physical quantity and a unit of measure are dimensionally consistent, the physical quantity service provides 2 functions related to checking the dimension. The first of them, called dimension of, takes a physical quantity and returns the physical dimension of that quantity. The second of these, check dimension, when given an instance of a physical quantity and the surface form of a physical dimension, will return the original physical quantity if it has that dimension. Otherwise, it will return null. We'll see how this can be very useful in one of our upcoming lessons where we're performing arithmetic with physical quantities, and we want to make sure that the inputs have the correct dimension. The last function that the physical quantity service provides for performing unit conversions is the normalize function. Given a physical quantity, it will put it into its normal form. This function comes in handy when you're accepting input from arbitrary sources where the units of measure might be in non-standard format. All of these functions make use of the physical quantity's symbolic representation of units of measure in order to put the units into the simplest form, derive the conversion factors from those of the simple units of measure, and to simplify the physical dimensions. You now have all the information that you need to complete today's lesson. Remember, you're creating an implementation for the parse observed lengths in feet function, which takes an observation and parses its value And if the unit of measure is length, converts it to units of feet. Otherwise, it returns null. Why don't you pause the video here and try your hand at solving this problem, and I'll be back with my solution. Welcome back. Let's take a look at a solution to today's exercise together. Now, I'm creating a implementation for the parse observed lengths in feet function. So I'm going to open up the function graph for that function. And I know that I'm going to need the parse observed lengths function that we created in lesson 2 and the unit conversion function. So I'm going to drag those in to my canvas. All right. Now I'm going to try and make sense of how I might connect these together. Clearly I'm going to want to take the observation that I'm given and parse that, so that seems like a good place to start. Now that gives me a physical quantity, and I want to convert the units of measure of that physical quantity. And that gives me a new physical quantity that should be in the units that I want, so I can wire that to the output. But let's take a look at the convert to function in a little more detail. It takes two more arguments. It takes a unit name and an optional precision field. I know that I want to convert this to units of feet, so I think what I need here is that foot function, which, if you recall, it should return the string literal foot. All right, so I'm going to send that into the unit name. So next I need to create an implementation for the constant function foot. And this is simple enough that I'm going to use the Lambda assistant to do that. All right. And we'll save that. And now everything should work. So let's give that a try. We'll give it an observation here. We'll use distance to runway and run that. And run. There we go. After a moment, it returns 237,602 feet. All right, let's try this with kilometers instead of miles. Kilometers, and run this. And after a moment, wow. Although that's probably technically correct, it's an insane number of significant digits that's being returned. And it implies that we actually measured this far more precisely than we probably actually did. So how do we fix that? You may have noticed that the convert to function has an optional argument, this precision argument, which takes an integer. It turns out that that argument controls the number of digits of precision that's returned. So we can wire that through from the optional precision argument here. It's that easy. And then we can run this again, passing it a reasonable number of digits of precision. And now we can see it's rounding to 3 digits of significance, which is certainly more realistic. Unlike rounding to the nearest decimal, using the digits of precision will work with very small numbers. So to demonstrate this, let's try 3 centimeters and parse that. And after a moment, we can see it returns a small number, and it still has 3 digits of significance. We can do some silly things here, just like we've done before. So if we try 4 kilogram meter per gram. So if you look at this, it's units of mass, units of length, and units divided by units of mass. So this should actually be a length. So let's run that. And after a moment, it tells us it's 13,100 feet. So what's really happening here? This turns out that 4 kilogram meter per gram is actually just a strange way of writing 4,000 meters. Because when you write this out and manipulate things symbolically, the grams occur both in the numerator and denominator of a ratio and cancel out. So you're left with km, or kilometers, 4 kilometers. And we can test this if we write go ahead and write 4,000 meters here and run this again. We in fact get exactly the same result. And there it is. So we've just demonstrated that the convert_to function is able to put units of measure, even in really unusual forms, back into their standard form. That's it for today's lesson. I hope you enjoyed learning about the unit conversion functions in the physical quantity service and are coming up with interesting ideas how you might use them in your next project. In our next lesson, we'll be talking about extracting physical quantity entity mentions from text documents. I hope that you'll join me then. If you enjoyed this video and want to learn more about the physical quantity service, don't forget to subscribe to the Mana Inc. YouTube channel